Transmission of nerve impulses. So, the nerve impulses are brought about by the movement of sodium ions, represented by the green counters, and potassium ions, represented by the blue counters. Okay? When a membrane is at rest, a resting potential is generated. Now, in this, a sodium-potassium pump pumps sodium out of the axon and potassium back into the axon. But what we find is that for every three sodiums that come out, only 2 potassiums come in. So what that means over a long period of time is that you end up with a greater amount of positive charge leaving the axon than positive charge returns to the axon. So what that results in is the inside being negative with respect to the outside. So in terms of a graph of membrane potential, what we have is our resting potential is starting down here in the negative region, and resting potential is thought to be measured at around minus 70 millivolts. Okay, so that's there. Now obviously that's just happening at rest, and so now we need to look at what happens when an action potential is generated. And so what happens now is when you look at the sodium and the potassium, you can see that there is a lot more sodium outside the axon than inside, and a lot more potassium inside than outside. Okay? And so what happens first is that a voltage-gated channel opens. Okay? And that voltage-gated channel is a sodium voltage-gated channel. And so what happens is that all of this sodium comes whizzing into the axon. Okay? So now that means that relative to the outside there is much more positive charge in. So we have now gone all the way up to around about plus 40, and the membrane is said to be depolarized. What that does is it then opens another voltage-gated channel, okay, and this time it is the potassium voltage-gated channel. So all of the potassium whizzes out, okay, and consequently returns the membrane potential all the way down back to resting potential, and then the process starts over. Now you will notice that here there's a bit of an overshoot, okay, and that is called hyperpolarization, and what that results in is something called the refractory period, which is a period of time where it is not possible for the membrane to be re-stimulated. Now what that means is, as you're progressing along the axon, if we've just had an action potential here, this area cannot be re-stimulated, so the action potential has to travel, it can't go backwards, which ensures only one-way transmission of nerve impulses along the neuron, which is obviously absolutely essential for the correct working of the nervous system. The impulses themselves are transported along the neurons by something called saltatory conduction, and what happens here is localized currents are set up between the nodes of Ranvier. So in this very schematic diagram of a neuron, you can see we're just drawing in the myelin sheath here. Okay, so if this node is at resting potential, that means it's going to be negative on the inside and positive on the outside, whereas if this one is having an action potential, then it's going to be negative on the outside and positive on the inside, okay? Which is going to enable the transmission of localized currents to move from one area to another, jumping along from node to node. And in those ways, nervous impulses can be transmitted along axons.